Hello, everyone. My name is Hannah Rosentrader, and I'm a manager of special projects here at the National Alzheimer's Coordinating Center. Really excited to welcome everyone to our data course session where we'll be covering all sorts of topics, including deep learning and machine learning, EHR data, using technology in our studies, and I'm really excited for all of the presentations coming up here. Without further ado, I would love to introduce Yorghos Tripodis. Yorghos is coming to us from the Data Course Steering Committee and from Boston University. Am I reading that right? So yes, welcome to our virtual stage. Yorghos, take it away.
Thanks, Hannah. I'm Yorghos Tripodis. I'm the current chair of the Data Course Steering Committee. I'm also professor of Biostatistics at Boston University and the data core director of the BU ADRC. I want to talk briefly about our work in the steering committee. First of all, I would like to thank Heather Allor, who is leaving our committee. She's rotating out. She has been a past chair of the committee, truly a mentor. I would like to thank her for all her work. Sudeshna Das from Mass ADRC, she will be the new chair. As I'm taking the role of the webinars. This is the way the Data Core Steering Committee is organized. And we also have a new member, Erin Abner, who is the incoming chair-elect. So she's next year, I'll be rotating out. Erin will be the new chair and we'll have a new member in our steering committee. As every year, we welcome any feedback. Please email us, communicate with us. Any member of the steering committee, myself, Sudeshna, or Erin would like to hear any kind of feedback you have, especially on how your ADRC was doing during the COVID period, whether problems that you keep having, how changes for the UDS4 may affect you and what you would like us to work. And we're going to have some poll questions just to help us on the way we organize our work in the steering committee. Again, feel free to contact us for any questions that you have. This year, we tried to talk about what should be our steering committee goals. And we came up with this list. We sent an email, a poll to all data core leaders and people involved with the data core. We had a questionnaire and we tried to come up with some goals. They will stay for next year, but obviously we'll try to update them as years pass by. So there were mainly two areas. One was, strengthening cross ADRC collaboration. So how we collaborate with different data cores from different centers, especially on two specific topics on method, tool sharing across center, as well as non-UDS data sharing across centers. And we're going to hear a couple of presentations later on the non-UDS data. So we'd like to, one of the goals for the steering committee is how we help this process across centers. So we don't really reinvent the wheel, but we share our experience. The second area of focus is improving data core ADRC operations within the center. And one area is how we improve data storage and analysis. One area, and we have heard about this, is the UDS4 and REDCap development. And we would like to have actually a steering committee or a subcommittee on the working group on the REDCap development for UDS4. And as part of your poll, there will be a question if you want to volunteer but also would like to talk about digital biomarkers. And again, we have an excellent talk later on, as well as how we link outside sources like EHR and CMS data. And again, presentation on that. And the second area is data core integration with other ADRC cores within each center. We know that the data cores play a very central role, but again, each center is different. So we would like to talk about best practices across centers, something that we would help us do our job better. So you should get a poll in your screen that please, as I go on and present the talks, you can fill in the poll. So we're going to have two sets of presentations. The first set, we're going to talk about deep learning and how it links with electronic health records. Colin Magdamo from Fall ADRC will give us the presentation. And the second is on digital biomarkers, mobile technology, and Rhoda and Honghuang Lin from Boston ADRC will give us the presentation. Each presentation is 15 minutes. Hopefully we'll have 10 minutes at the end where Deborah Blacker will direct the discussion before we move to the second set of the presentations. There. Where we will have two very interesting presentations on machine learning, so really new analytic methods, but how they relate to outcomes that we deal in our ADRCs. One is on MRI predictors, and the second is on A-beta status. From the first one from Ramon Casanova, and the second from Honghuang. And again, we'll have hopefully a 10-minute presentation before we finish where I can moderate the discussion. So without really waiting more, I would like to introduce Colin, who's going to give us the first presentation.
Thank you very much, Yorghos. So let me share my screen. Okay. And is my screen visible?
Yes.
Great. So I'm Colin Magdamo, and I'm going to be talking today about active deep learning to detect cognitive concerns in electronic health records. So there are three general questions I would like to tackle with this talk. The first is, are clinical notes useful in identifying patients with cognitive concerns? The second is, what kinds of natural language processing models can effectively leverage clinical text? And the third is, how can we address biases in training data via an active learning approach? I'll start with the background. Dementia is under-recognized and under-coded in claims data. Nonetheless, information on cognitive concerns is often found in unstructured clinical notes. On the right, we see a flowchart that begins with an underlying change in cognition. After this change in cognition, the patient or their family would notice or relay a concern, and then report to an MD. Once reporting to an MD, that MD would chart free text in electronic health record. After that free text is charted, then potential structured variables in the EHR would also be logged. This includes things like problem list diagnoses and medications. Finally, there is a potential claims that would get encoded. Along the way, there is also an opportunity for a specialist referral or consultation. An important aspect to keep in mind is that there's no guarantee data would be logged at any of these steps. So it's important to utilize every possible resource of information when trying to predict changes in cognition. Manual review of clinical text is time-consuming and often prone to errors due to the sheer volume of text that needs to be parsed. Automated mining of clinical notes presents a potential opportunity to label patients with cognitive concerns who could benefit from an evaluation or be referred to specialist care. Another use case is to provide better phenotyping for research studies using electronic health records. I'll now talk about our gold standard dataset comparison to claims. Our cohort was constructed by Dr. Lydia Mora and colleagues. It comprises of Medicare beneficiaries within the Mass General Brigham Accountable Care Organization, or ACO. This cohort was 65 years or older as of 12/31/2016, and it was sampled equally from 3 strata. The first was at least one dementia-related ICD diagnostic code. The second was evaluated by a dementia-related specialist, but no dementia-related diagnostic code. The third was neither of the above criteria were met. Each of these 942 patients was adjudicated for both cognitive concerns as well as a syndromic diagnosis. Then we constructed our own binary cognitive concern present label by asking, does a given patient have cognitive concern, MCI, or dementia? On the right, we see a comparison of dementia-related ICD codes and medications with gold standard labels. Of particular interest is the fact that of those with cognitive concerns that truly were present when adjudicated by experts, 29% of those individuals do not have a dementia-related ICD code or medication. This implies that relying on diagnostic codes and medications alone is not sufficient if you wish to classify or categorize whether or not a cognitive concern is present for a patient. So how do we mitigate this problem of low sensitivity when relying on structured features alone? One of the potential answers comes from utilizing NLP models. The first I'll talk about is a lasso regularized logistic regression using regular expressions. Here we see a figure that has several different regular expression categories. These categories were obtained from a study led by Dr. Gilmore-Bykowski. We notice first that in the medication category, 40% of individuals with a true adjudicated label of cognitive concern had at least one match to this medication category. Contrast this with the blue, which is no cognitive concern labels. Less than 5% of individuals with no cognitive concern have at least one match to the medication category. This implies that there is some inherent discriminatory power in counting the number of times terms that map to this medication category appear within an electronic health record. On the bottom is the model performance when we use the counts of the regular expression categories. We see that we achieve adequate performance, but we can still do better. The reason why we can do better is if we turn to the cognition category on the far left. Here we see that nearly 80% of individuals with cognitive concern have at least one match to this regular expression category. However, almost 65% of individuals with no cognitive concern also have a match. This implies that cognition and terms related to cognition have high value presence in unstructured text, yet it's the context with which these terms are used that allows us to inform or discriminate between cognitive concern and no cognitive concern. Now I'd like to talk about how we can build upon this NLP foundation via deep learning. We have 3 sequences at the top. The first, or record 1, says, based on detailed report, intact cognition, no prior history of CVA. This is an example of a sequence where no cognitive concerns are present. In the second record, we see a sequence that reads, an 81-year-old female who presents to PT with impaired cognition. This is an example of a sequence where cognitive concerns are present. The third record is an example where cognitive concerns are not present, and we also don't have explicit evidence of cognitive concerns. The record reads, mother had cognition problems in her 70s. The reason why this is labeled neither is because the information related to cognition is not actually describing the patient in question. It's describing their mother, a family member. This goes on to become an inherent challenge when using NLP methods, but deep learning provides a potential solution. What deep learning allows is for every sequence to be embedded into a numerical vector. The idea is that this numerical vector would convey inherent semantic properties of the sentence that was the source of input. Once we have a long vector representation, we can apply dimensionality reduction to actually get a visualization in 2 dimensions. This implies that sentence embeddings can discriminate the presence of cognitive concerns. What we've done is we've applied the previous method to 150 sequences that were taken from patient charts and were also labeled by experts. On the left, we see the projection into 2 dimensions. There are 3 labels here. Red is cognitive concerns were present, green is no cognitive concerns were present, and blue is neither. What this implies is that clear clustering patterns can emerge. While there is some overlap between the different cognitive concern classes, we see very good separation between these 3 categories. This is because contextual information in the sentences are being utilized to generate these embeddings. This is a stark contrast to the regular expression methods, where we're simply counting vocabulary terms. When we only count the presence of a keyword, we have no contextual information as to who that keyword applies to or where it's being utilized within a sentence. With deep learning methods, we're actually able to integrate this information into a single numerical summary of what is being conveyed in the textual patterns themselves. The previous slide was talking about encoding a sentence or a small textual sequence into an embedding. However, we're actually interested in the binary classification of the patient and whether or not they do or do not have cognitive concerns. This means that we need to aggregate the sentence level embedding and classification probabilities up to the patient level to actually be utilized. In order to do this, we have a data set that is a subset of our gold standard with at least 5 encounters. This results in a cohort of size 882. This is further split into 70% train, 10% validation, and 20% testing data sets. The sample characteristics of this cohort are displayed on the bottom. I'll now discuss some of the results that arise from this deep learning approach. In item A, we see an ROC curve that compares a baseline model that utilizes only the medications and diagnostic codes as input, and contrast this with our deep learning approach. We immediately see an appreciable difference, a large benefit of utilizing this deep learning approach towards classifying the binary cognitive concern. In item B, we see the rest of the model metrics that compare the performance of our baseline model to our deep learning model. And in C, we see classification probability densities that are performed on our held out test set of size 177. Note that there is some overlap between these two densities. This implies that while our model does have discriminatory power for our 2 labels of interest, the problem is that both of these densities are overlapping in the middle region. These are individuals or observations where the model is confused about what label to assign. There is large ambiguity due to the representation in our training set. We can then utilize an active learning approach to combat this issue. Active learning is an approach where we begin with a model. We have our initial model that was trained on n equals 882 individuals, and we train, validate, and test to arrive at our initial model setup. The question then becomes, how do we improve the performance of this model? The natural conclusion is to add observations to this gold standard data set, but is there a heuristic we can use to decide who to add? The first approach is using the predicted probabilities of our model itself to generate an uncertainty score. What we're able to do is look towards the full MGB ACO cohort of 105,000 individuals, use our initial model to predict the classification probability of cognitive concern, and then assess this probability via a scoring system that says we can generate an entropy or uncertainty measure based on how far the predicted probability is from 0.5. We can then utilize uncertain examples and prioritize them for expert labeling. When we prioritize them for expert labeling, we are training our model in the most efficient way possible by focusing on the least certain observations. Once labeled by experts, we can add these back to our gold standard data set, thus improving our model performance. Another criteria of interest is diversity. In order to achieve diversity in representation of our sample size, we can then cluster all of the structured features of the full 105,000. This is a screenshot of an active learning tool that can facilitate expert labeling. I'd like to call attention to this aggregated probability of 0.5765. This probability implies that this is an uncertain patient example because the probability is close to 0.5. The model is uncertain. Is this an individual with cognitive concern or without cognitive concern? This tool allows an expert labeler to efficiently adjudicate whether or not this given patient does have concern or does not have concern. They can prioritize individual notes or sentences that have very high classification probabilities. In this example, the classification probability of this particular note was 0.98. This means the model is reasonably confident this note pertains to cognitive concern, but is unsure about what the entire individual is when trying to classify that individual. If we read the text, we see living situation, lives with his wife, she has significant cognitive impairment. What this implies is that the model is predicting a very high probability because it is confused as to who actually has this cognitive impairment. It should be attributing it to the wife, yet it is actually attributing it to the patient. This introduces noise into the overall aggregated probability, and shows that there is room for improvement in adding this patient's correct label to the full machine learning setup. Here, an adjudicator can select no concern on the left and submit this via an easy one-click interface. By submitting this label, we can add it back to our gold standard data set, thus improving our model performance instantaneously by focusing on this uncertain patient. We can then collaborate with our clinical core to ensure that we have expert adjudication in combination with our data core, who can build tools such as this to investigate what our model is actually outputting. I would also like to talk about addressing diversity in these gold standard data sets. The most recent Boston census states that almost 45% of the entire population is a racial or ethnic minority. However, our initial cohort that we used to train was 92% white. The full MGB ACO cohort contains 105,000 individuals to select from. We can use demographics combined with other structured data to sample diverse patients. In this fashion, we can oversample underrepresented groups along several axes. In addition to demographics, we can use clinical variables, such as the overall volume of care a patient receives. On the right, we see another projection in the same style that we've seen prior to this slide. Red dots are patients that were in our initial cohort of 882. Gray dots are patients that are in the full MGB ACO. As you can see, we currently have not fully explored every potential area in this two-dimensional projection. What this means is we do not have adequate representation of every possible combination of the structured variables within the full cohort. By exploring the rest of these clusters and promoting expert adjudication of those that we have not seen yet, we can bring the representation of our final gold standard data set up to parity with the full population we are trying to model. As a summary, natural language is an incredibly useful tool for improving sensitivity in machine learning models that classify presence of cognitive concerns. We would like to directly add structured features to our model to additionally improve performance. We would also like to increase our sample size, add diversity, and improve model performance via an active learning approach. Our future plans for generalizability include collaborating with Dr. Andrea Gilmore-Bykowski at University of Wisconsin-Madison, as well as Dr. Carol Brain at University of Cambridge, among others. I'd like to acknowledge the following contributors, and in particular, Dr. Deborah Blacker and Dr. Sudeshna Das. Thank you very much.
Thanks, Colin. I think we should move to the next presentation. So Rhoda, you're first.
All right. Although Colin, that was great. Just want to mention that.
Thank you.
All right. So sorry, let me just restart here. Okay. We are in the home stretch. So today I'm going to provide a brief introduction into the types of applications that are currently available, both in the clinic and then also remote assessments through mobile devices. And this will start to highlight some of the assessments that we're considering for UDS 4.0 using a platform such as Linus Health, which actually was presented yesterday as part of the UDS tech panel. So just to get started, so what is being illustrated in this video is actually a range of the cognitive assessments that we're considering in an ADRC pilot study, which will initially happen across about 6 centers. And it will start focused on in-clinic assessments, where we will really focus on the tablet and include types of assessments that, pretty much anybody within an ADRC will really well recognize as, standard neuropsychological tests. And we're going to capture digitally both the written and the spoken responses. And then we can potentially move to remote options, largely, again, centered around a smartphone, because it is the most internet-connected technology that people are likely to own. And so what you can see is it includes the same range of assessments that are pretty well known, covering all the major cognitive domains, and includes capturing measures of screen-based behavior and also a number of voice-elicited responses. And so I think, though, what's really important to emphasize here, and this is actually really only the beginning of where we're headed. And so it's really kind of what I think is the start of our digital future. So in this video, we're actually trying to highlight a bunch of other options, really in the form of wearable devices. And these are things that can be used both in the home or in the clinic, and certainly on the smartphone as well. So at the BU ADRC, we've been actually proactively exploring sort of a whole range of other possibilities for expanding our digital footprint. And to this end, we're continuously looking for existing and emerging technologies that can really help us move much more deeply in our phenotyping, both of AD-related behaviors, as well as clinical metrics that are related to them. And we've actually started to assemble a document that can provide an real idea of what are all the options that exist. And we're going to look to post this document actually online, invite all the ADRCs to add technologies that they may be using, that they're considering using, that they've seen and thought they should share. We really want this to be an informational resource. Now, I just want to point out that this document isn't meant to really be comprehensive. That's actually really hard to do because of the breadth and depth of technologies. It's pretty expansive already. It's continuously changing. It's growing rapidly, and that's actually worldwide. So our purpose is really to put forward some representative technologies, have our ADRC community continuously contributing ones that they find, and really provide a resource to each of the ADRCs so they can really tap in and figure out to what extent they want to integrate technologies well beyond what we might be recommending for UDS 4.0. So let's see. Now, because there's so many technologies out there and more emerging like every single day, choosing technology partners actually requires some decision making. So, what we tend to do is a lot of what I call active engagement technology, and that usually involves subject burden, but then we have to worry about our elderly participants. How comfortable are they in engaging with digital devices, including their smartphone? But then we contrast that with passive engagement technologies, which certainly reduce burden and use, but then also raise the issues of privacy and intrusiveness. Now, there's also the issue of how much do you want to rely on familiar metrics, such as, derived measures that, we're traditionally used to using in our analyses, versus how important is it to have raw digital signal files? Now, here's the thing. No matter what exists right now, and I don't really care what it is, the best of the best, whatever that might be, it's going to be obsolete. And it's going to be obsolete quickly, probably within 6 to 12 months. It turns out version 1 of nothing has ever stood the test of time. So how do you future-proof against quick obsolescence is really something that you have to worry about. And then what you have to do is you have to balance this across a number of different competing factors. So there's the ease of use. So for instance, consumer grade technologies are very easy for participants to use. But here's the thing, they tend to give you lower quality data. And it turns out that devices that give you research grade data tend to be harder to use. And then there's the whole issue of open source API. How well does this technology talk to other technologies, or it's open to, alterations, right, to its code, and for instance, how much is it going to give you the timestamp features that maybe an original application won't give you, so that maybe you can pull it out yourself. And so then there's the issue of the value proposition. And what I would say is that this isn't just limited to you. I actually think it's more important to think about your participants. So this gets back then to the ease of use issue, right? Because consumer level features are certainly made to, much more attractive to participants. But, if you do that, then you're going to have to balance that against the quality of the data. And if you're trying to get a cut rate on the technology itself, it's going to be, what is the value that you bring to your tech partner? So they'll want to keep working with you and do it either at or at even below cost. Then another issue is scalability. So in clinic really allows you lots of control But it also ensures that you have internet connectivity, but it also limits what you can do. And scalable technologies can usually collect large amounts of data at low cost, but it comes with this trade-off. And of course, there's the issue of costs. So in-clinic will always cost more than remote. And so once you sort of get through this issue of which, who to work with, then you have the issue of, data harmonization. So first of all, there's lots of competing devices. So are you going to do a bring your own device strategy, which means dealing with data harmonization on the back end? But also the problem is, as I noted, version 1 of nothing is going to last. So no matter what you're using, it's going to be upgraded. And that's going to be another issue for harmonization. And then this is assuming that the company remains viable. And the reality is there's a really competitive tech world out there. Companies come and go all the time. Even big companies fail. If anybody remembers Compaq or Sun Microsystems, huge companies that actually no longer exist. And then there's the issue of acquisition. So, WhatsApp, LinkedIn, even Sprint T-Mobile merger, which is largely T-Mobile taking over Sprint, new owners are going to set new rules. And so now with all this digital data comes the need for digital signal processing. And Honghuang will talk a lot more about the realities of digital data management processing, but I just want to highlight briefly, just using digital voice as an example, there's decisions to make about to what extent you want to stick to absolute accuracy of data files. So in the case with digital voice, precisely separating out examiner and participant responses and being absolutely accurate about your speech to text translation, which a lot of NLP, by the way, relies on, but very labor intensive and very costly, versus what's your comfort level with automated methods. It's really about the degree of perfect taking precedent over good. And as some of you might have heard during, the earlier tech presentation, it turns out sometimes good produces results that end up being pretty comparable. So what I'm going to do now is stop, and I will turn the session over to Honghuang. But first, I want to give a special shout out to Spencer Lowe and Zach Pop, because for their tireless work, they've really helped me put together these videos since I've yet to master iMovie. Thank you very much.
Okay, great. Thanks, Rhoda, for the introduction. So in the following slides, I would like to discuss about the management and processing of digital data. So we all know the potential of digital technology for cognitive monitoring. But one issue with digital technology is that it generates a huge amount of data, sometimes too much for us to handle. So it's important to think about how to transfer data from digital devices to computers or servers for downstream analysis. We also need to think about the data storage, because all different data might have different data formats and require different storage space. The digital data will also more valuable if we can share the data across the world. And so we have to consider what to share and how to share. And most importantly, data security is always the first priority when we consider the data sharing. One thing we have to consider is that there are different technology might generate different data types. For example, from digital pen, we might have a CSK data format. It will record the entire process of drawing. So it will also input a time step at each individual step. For digital voice, we might use the view format, so we can replay what the participant just said. For the neurometric data, we might use Excel format. So for each data type, we have to develop a corresponding analysis pipeline to process the data for the downstream analysis. Also, data all come from different file sizes. For small files, we might be able to put into the CD disk or like external hard drive. For large data, we might have to put on specific storage server. In recent years, we are also increasingly use cloud-based storage. We are partnering with Alzheimer's Disease Data Initiative, or ADDI. It's a cloud-based service based on Microsoft Azure Cloud. So it can provide a convenient security data storage solution for our digital data. One thing we would like to emphasize is that for the digital technology, we might just use one collection, but can generate multiple data sets. As Rhoda mentioned, for the digital voice, we might just use like the full recording data, or we might first perform diarization first and only use the voice recording from the participant. We might further derive other features from these recordings, like acoustic features, syntactic feature, lective feature, to reflect different aspects of the human voice. And then we might use these feature sets for the downstream analysis. All these data sets are actually derived from the original digital voice. So it's important to build a data tracking system to link all the data sets together. And similarly, for the raw digital pen data, we might also derive different features, like what's the total time the participant used to draw the clock, what's the percentage of time that used to think when he or she drive the clock, and what's the longest latency. We might also ask if what's the size of the clock, is the clock face circular or not. For Apple Watch heart rate data, we might calculate the average variation of heart rate data within the entire hour, or during the exercise, or during the recovery period. Also, we might calculate the maximum and minimum heart rate data during the study period. So all this can provide different features from the digital technology. Also, the data will come with different scales. So we have to first perform scaling to make sure that the data are comparable. And similarly, main data might be the distribution might be skewed with a long tail. So we might need to perform normal transformation to make that normal distribute. Missing data is usually a big issue for digital technology. There are many reasons that can contribute to the missing data, like loss of internet connection, run out of battery, or lose connection, or simply because we forget to do the test. Here shows like an example of number of minutes in exercise recorded by Apple Watch. Sometimes we might just forget to charge the Apple Watch, so we might not have the information about the exercise in those days. But on the other hand, most data analytical approaches assume complete data. One way is just to simply exclude any samples with missing data, but it might cause a big loss of sample size, and it also can introduce some statistical bias. There are several methods that have been developed to impute the missing data, like simple random imputation, or model-based imputation, or multiple imputations. Each of these methods has its own advantage and limitation. So we have to explore multiple methods to figure out what will be the best one for our data set. And also, digital technology might generate a lot of features. Many of them might be redundant or unrelated to the outcome of interest. For example, if we want to predict the body weight, the leg length might be highly correlated with our height, so it can be considered as a redundant feature. Our favorite music probably has nothing to do with our body weight, so it can be considered as an unrelated feature. By doing feature selection, we will be able to generate a simple model. Usually, a simple model is more powerful. We can also reduce the overfitting, especially when we have much more features than the sample size. But this is usually the case for the digital technology study. We can also lower the noise level by feature selection. Unlike a clinical-based test, digital technology also provides a convenient way to perform repeated measures. So participants don't need to schedule an appointment or try all the way to the clinical to perform a test. We can simply do the test at their home. Here shows an example of standard cognitive test in our pilot study. So we ask participants to perform the test at a baseline and also every 3 months within 1 year. As you can see, all the tests has a decline participant rate. So people usually have more interest at the beginning, but the participation rate continue to drop. So we have to take it into consideration when we perform digital technology analysis. And lastly, I would like to emphasize that digital technology alone won't solve all the problems. So we have to integrate other data modalities like neuroimaging, clinical genetics, blood biomarkers, and develop advanced statistical methods to integrate all this information to better understand it. That's all I have. Thank you for your attention.
So I'll give the speak to Deborah, who is going to lead the discussion. We only have 7 minutes, though. Just
Right. Okay. So I'll be quick. First of all, I'm going to start with the last 2 because there weren't questions posed in the chat anyway. Those were, and part of the reason is they were really a tour de force. Thank you both so much. That was quite amazing. Rhoda, I really, really appreciated how much you emphasized all the pitfalls and that there are places you can't win, so you have to choose your best compromise, and maybe some harmonization of which compromises people choose where it really matters might be in order. And Honghuang, sort of thinking about both the structured variables that you can get out of these, but also how you can get things that you were too dumb to ask, but the machine can see. I really appreciate it. So thank you both very much. And Colin and I agreed in the chat that I would answer the other questions because I'm a little bit of a ringer here since I also worked on this project. So, and you guys asked exactly the right question, no surprise here. The idea was that this was a first step. So in the clinically adjudicated data set, we do have severity indicators, which by the way, exceed what you can get in claims. Not that even claims don't even try to do severity indicators except dementia or MCI, but we have subjective complaint kind of diagnoses, MCI, mild, moderate, and severe dementia. I should say that the gold standard is anything but gold because this is doctors reading medical records. It's not doctors reading research data. And if any of you have been in a consensus conference, you know that even when doctors read research data, these are hard things to get really good agreement on. But nonetheless, there is information in what doctors get out of that. And we also have, confidence levels for the doctors so that you can limit it to places where the doctors are confident. And the next step is to do just what you're asking. We have every reason to think that will be harder, with the caveat is that it's fundamentally ordinal data. So we have the option to use ordinal statistics, which might help a little bit. But the first pass was, can the computer find people where there's some level of concern or not? And that has some value clinically, like we're talking about collaborating with primary care to augment screening with this. And somebody asked which kind of notes. We've focused on clinic notes, but there are actually a lot of information in PT, OT kind of notes, some other structured variables like missed appointments or unstable lab values. So there's a lot. Ellen has a question. Is there time for one more question to the last two folks? So from Ellen Weissman, forgive me if I read aloud for you. Rhoda, did you just want to answer it online then? I was trying to pay attention to the talk, so I didn't want to answer online.
I was actually kind of typing it.
I saw that you were typing, which is so. Yeah. So Ellen, I'll let Rhoda answer, and that will get us to the next one. Or do we have a break, Yorghos? You're our boss here, so we have to just do whatever you say. You and Hannah, that is.
I think Hannah goes, but anyway. So I think we can. We have 4 more minutes if we have.
Okay. I think that it's Friday afternoon wherever you live, so it probably would not be so bad if we just moved on and not try to use more time. Rhoda, thank you for answering Ellen in the chat.
Yeah, so I think my main concern is always our presumption that the paper version is the gold standard, because they already have a lot of limitations as well. So I think, and I'm always very wary about us trying to take our digital and fit it into what we already knew in the past, because the whole point of digital is actually to move us in directions that we haven't really been able to go. But having said that, we do want to make sure that the data is certainly going in the comparable directions, has comparable distributions, et cetera. But I do think we have to be very careful about thinking that what we did is what we're trying to replicate, just trying to do it digitally.
Yeah, and I think that, there's a big psychiatric literature on this, because the gold standard is always, trained clinicians. And of course, trained clinicians are full of error and ambiguity. And this is not an EHR. This is like talking to the person in real time. Right. And so I think in any setting, it's this triangulation where you absolutely do want to make sure that it can do as well as that. But you also, when there's, and people, for instance, in psychiatry often use the kappa statistic, which is a reliability statistic, instead of a validity statistic, for that very reason, because they sort of recognize that some of the disagreement is that the new version is actually better. So you're sort of saying, you're just being neutral. When do they disagree? And then you look at the disagreement and try to understand it. But there's a very large literature on this in psychiatry, because we have so many imperfect measures of so many stripes. So anyway, thank you, everyone. That was a lovely session. I think we should move on and let everybody start their Friday afternoon, or on the West Coast, catch up on their neglected email or sleep.
Yes. Thank you, Deborah. Thank you, the presenters. It was a really great presentation. So let's move on. The next one is Ramon Casanova from Wake Forest ADRC. He's going to talk about comparing machine learning derived and hypothesis-driven MRI predictors in cognitive impairment for the ARIC study. So Ramon, the floor is yours.
Thank you very much for inviting me to give this talk. My name is Ramon Casanova. I am associate professor in the Department of Biostatistics and Data Science at Wake Forest School of Medicine. I am going to talk about work we have done on early detection of dementia using machine learning and structural MRI. First, I want to acknowledge my colleagues at Wake Forest that they have helped me during the years. I supported my machine learning research. Also, colleagues for the ARIC group and in the NIH, and also the NIH and the Alzheimer Association for Funding, and the ARDNI, ARIC, and the Women Health Initiative memory study for access to wonderful data sets. As we know, the community is actively searching for different biomarkers for early detection of dementia. We are looking at different sources, different type of imaging, CSF biomarkers, and now the blood biomarkers are very promising. Some colleagues are looking at eye data, gait information, and of course omics. We are going to talk today about a structural MRI. The structural MRI provides a correct image of brain structure, and it is used as a biomarker of brain tissue atrophy. Compared to other imaging modalities, it's more available and less invasive. We quickly want to touch base about this important work done more than 10 years ago by several groups in US and England. This work was based, on support vector machines. That is a machine learning approach that was very popular back then and still is widely used. And some scores were proposed that what they do is, given the scan of an individual, they summarize the severity of the abnormal pattern present in the brain that could signal dementia risk. We follow a different approach. We propose elastic net, regularized logistic regression, and we propose the Alzheimer's disease pattern similarity scores. Some general characteristics of the approach is that the voxel is a voxel-based approach, which this implies this high dimensional because each voxel in the image could potentially be variable in the model. And the sparsity property of the elastic net implies that the procedure is able to select by itself the brain areas relevant for prediction. So we have estimated and validated the ADPS score using MRI data from ADNI, the Women Health Initiative Memory Study, and ARIC. The basic element to estimate the score is, well, we first need a training data set containing MRI scan of clinically well characterized cognitively normal subjects and AD patients. At this point, we are using around 600 images from ADNI. And we need a target data set containing MRI images for which the ADPS scores are intended to be estimated. And then we need image processing tools, because we need to align the images of both studies and also segment different brain tissues of both of the training data set and the target data set. We use for this the advanced normalization tools, a software with cluster computing. And once this is done, well, we have to train a machine learning classifier based on the elastic net, as I mentioned before. And then the data, the imaging data from the target data set is provided as input to the classifier, and the ADPS score are generated. We did this first for the Women Health Initiative Memory Study. Keep in mind, these studies, the WINS MRI and ARIC and also ADNI are they contain large MRI databases. So WINS was conceived to investigate the impact of hormone therapy treatments on brain structure and function, and the study has a follow-up of more than 25 years. MRI scans were collected at 2 time points in 14 clinics across the US. The first scan was collected from more than 1,300 women, and the second scan was collected from more than 700, with an average follow-up time close to 5 years. We reported results from WINS in Neuroimage and other journals We found the score to be associated with age, cross-sectionally and longitudinally to cognitive function, cognitive status, air pollution, mortality, and other findings. And then more recently, we apply the same procedure that I explained to ARIC. This study enrolled at baseline more than 15,000 participants, mostly white and African Americans, aged between 45 and 64 years. ARIC is a deeply phenotype study with more than 30 years of follow-up. The study collected close to 2,000 MRI scans during visit 5. That was between 2011 and 2013. And also detailed cognitive assessment with adjudication. Participants with MRI scan and visit 5 that returned to visit 6 also received a full cognitive assessment. And the average follow-up time was also close to 5 years. So we confirmed several of the findings made in WINS, association with age, cognitive status, incident cognitive impairments, and others. But we decided to do something different. We wanted to compare the ADP scores. This is a measure created using machine learning and Bose-based with another one, which is hypothesis-driven, volumetric, meta-ROI composed by areas susceptible to a D in the temporal and parietal region. And this was available in ARIC. We wanted to compare these two measures as predictor of incident cognitive impairment between visit 5 and visit 6 of the study. So for this, we have 839 cognitively normal participants. I want to highlight that this is more than 30% of the participants were African Americans. Then to evaluate the prediction of incident cognitive impairment, we used tenfold cross-validated logistic regression and the area under the curve to assess performance. And we did that with a full sample of 839, and we also did that across different stratification of the data across race, sex, and ApoE epsilon 4 carrier status. And we found that in all occasions, the performance was higher when we use the ADP scores. We also did an association analysis where we use logistic regression adjusted by age, education, sex, race, and intracranial volume, but including in the model both measures. And we found that the meta-ROI in the presence of the ADP score became non-significant in all occasions. And in addition, we performed a random forest analysis, including 28 predictors from different domains, demographic, clinical, cognitive, MRI, and ApoE to investigate the relative importance of the two measures based on the random forest permutation index. And as you can see, the ADPS was not only more important for prediction than the meta-ROI, it was really the more important variable among the 28 included in this analysis. And to finish, I'm going to touch briefly on this. This is a very recent analysis I did with my colleagues in the ADRC. We use the same classifier we use for ARIC. So we obtained this result. This is cross-sectional, a sample size of more than 500. The average age is 70 years. And we had the opportunity to compare here with a different meta ROI. In this case, is a meta ROI composed of temporal regions, of areas in the temporal region, this time using the average of the cortical thickness. Before we used volumes. And we also have the hippocampal volume. And so we build the ROC curves, and in this analysis, the ADP score perform better than the other two. For future work, we intend to deploy actively these measures in our ADRC and look for opportunities to extend across the ADRC network, imaging center and large clinical trials. Based on machine learning and artificial intelligence, develop other measures that could allow further assessment of dementia risk and brain aging using other type of data. And I wanted to thank you for your attention. If somebody is interested in this, feel free to approach me. I'm looking for collaborators across the ADRC network. Thank you so much.
Thank you, Ramon. That was an interesting application of machine learning for prediction. Let's move to the next presentation. Shan, again on machine learning, but on a different outcomes. So the floor is yours.
Okay, thanks a lot. So yeah, so I think this we try to use the machine learning to predict the amyloid status, and we try to use the domain score instead of the overall score. And here's the history. I was involved in the Nevada ADRC before moving to Florida, and also we are central candidate at Biostatistics. We were supported by the CTSI as well. And this is the work will be multiple people from the ADRC and from Nevada. We were involved, and also involved a clinician from University of Washington as well. And Dr. Bennett and all the others, they help us a lot why we are doing that. So the idea was started whether they always found when they see patients as a clinician, they said normally they normally look at particular scores. They do not look overall scores. They do not look at overall scores, but particular scores are more important to them. So that's basically the beginning of the project. So then we did some logistical regression, try to differentiate the people with amyloid positive or not, and then and we submit a poster for that. Then later on, I think we decided to do. We probably should more further improve that. Then that's what's the beginning of this project. We try to use machine learning. And I think that's the reason I explained. So basically, we want to see the difference between the total scores and the domain scores from each scores. And we hopefully the domain scores from MOCA or like the ADS-COG or the MMSE would further improve the prediction, because at the beginning, we just used the total scores and we used the logistic regression. The results were not that great. And the reason we are studying amyloid, like amyloid is the target for many drugs for Alzheimer's disease related. So they are one of the two pathologics. So one is amyloid beta, the other is tau. And so for the amyloid beta, so there are a couple of famous drugs, which one of them obviously is aducanumab, which has been approved now. And also the second one is the BAN 2401, and there are many other drugs still ongoing. So normally the amyloid beta status can be determined using two ways. One is use CSF, second use the PET image. And we use the ADNI data, so we use the PET image in this case. And the importance of amyloid, we just want to identify the individuals who are more likely to have the AD in the later on. So that's make the significance of this project. So this is basically the relationship between the total score and the domain score. You see the total score for the MOCA is 30, and they could be separated by 7 different areas. So the spatial score, the naming score, the attention, the language, the abstraction, the delayed recall orientation. So, and even though the sub score, sometimes the range is so small, a statistician would argue if the range is from 0 to 3, so probably we cannot consider as continuous, it's ordinary and all the other things. So, and And so also in the Alzheimer's disease, everybody knows Alzheimer's disease, the patients are heterogeneous. They're not homogeneous. Male and female are different. So normally people will find is female, if they have the Alzheimer's disease, they're more likely to decline much faster than the man with Alzheimer's disease. And also the ApoE4 carriers, it was being found that they were more likely to decline faster, and at the beginning they already been getting worse. And so they are. So that's the overall benefit. We want to separate the population into multiple, basically stratification. So we have multiple groups instead of we mix them together, and we may not be able to find what's the difference actually come from within each group. So here's the machine learning already being mentioned by multiple presentation today now. So there are many. So when you look at we use the R software, statistics software R, and there are many packages over there. And one of the packages you can see they're like probably tens of thousands, no, not thousands, hundreds methods, including like use different sub methods. So this is the commonly used ones. You could use decision trees, the clustering, the simple logistic regression, everybody knows, and all the linear regressions, the Bayesian methods, and some of the boostings, and like SVM, people normally use a lot, and the PCAs and the ordinal least squares when you have the outcome as ordinal. So there are many methods. And overall goal is we try to identify which machine learning method works the best. In other words, meaning have the highest accuracy to predict the amyloid status within each subpopulation. And we use the K-fold cross-validation resampling approach. And the third point is we try to make is, we think instead of just doing one time, you're doing K-fold cross-validation, you probably should do many times. So this is basically we introduced in the paper says, you probably should do a Monte Carlo simulation. So basically the idea is for each time you would get the K-folders, and within that set, then you're doing the cross-validation within that K-folder. That's the basic idea we propose to say. So this is the ADRD that we use the ADRD data, and we try to use the NACC data as well. Somehow the NACC data did not collect all the information we wanted, but we are working on now without that information with the model can still have the similar results. So we use basically three group of population from the ADRD study. One is the individual with significant memory concerns. So they were selected from ADRD 2 and 3. So ADRD from ADRD 1, ADRD Go, ADRD 2, and ADRD 3. So we only selected them from 2 and 3 for the significant memory concerns, because that question will be added later on, not at the very beginning. See whether they have the memory concerns. That's the subgroup. And also the early MCI and the later MCI. And they were from the ADRD Go and ADRD 2 and ADRD 3. And actually the population selection will be a little bit complicated because sometimes they don't have the measurement here and they have there. So we spend a lot of time to finally choose the population we need. And amyloid status, normally we use the PET image data. So basically the traditional way is the standardized uptake value ratio as the cut point of 1.11. Obviously, you could use other ones, use 1.1505, but this is normally commonly used one. In the model, normally, so in the model, the outcome is binary in here, and the amyloid status, and the features selected here. So basically starting with the demographic, the age, race, the year of education, and whether what's your marriage status, and all the other information. And we separate there by the sex and ApoE4 status. And for the cognitive test, we use the CDISB, which is normally commonly used in Alzheimer's disease clinical trials. So we include that. And the MMSE, MCOG, ADS-COG, we use the 13 version. And we also including their subscores as well. So, and here's some of the brief results you can see. So basically, here's the 15 different machine learning methods. Because we don't have enough space to show what they exactly are. And so the line here is basically as the number of features increase. So the features we first, because for example, if you have 50 features, right? So then you probably have the total number of possible combination of features is the power 2 to the power of 50. That's a huge number. So then I think at that time we decided to do which is called a stochastic ordering. Instead of doing all the possible combinations, we first do individual fit and find which one had the smallest p-value, consider as the first feature, then followed by them. So basically we use the p-value to sort them and then add them up. So that's basically look like. So as you can see, so within the female for the this is the group of the late MCI group. And so as the feature goes on, so you can see the average, the maximum for the female is around 85% accuracy. But even though you have more features, they're not adding on that because the more validation as well. So it's not working. For the male, only around like 78%. So there's like probably 66% difference in here. Later, I will explain what exactly the machine learning method are being identified and what are the features being identified as the ones should be used in the model. And for the early MCI, the predictions are not as good as the later MCI to predict the amyloid state, especially for female. Used to be around 86. Right now it's around 70%. It's pretty low. And for the male, it's similar. Used to be around 80%. Right now it's kind of a little bit lower, but not too much. The great finding is from the SMC group. The group have the memory concerns. So for the female, it's not good. The prediction was not great. It's around even below 70% in general. But for the males, actually, it's great. It's almost close to 90% for the males. So we can use that model to pretty certain that the male may have a positive amyloid status, positive. Here is the identified one. So we separate the group by the diagnostic results, basically memory concerns, early MCI or later MCI, and also stratified by the male sex, by male or female. So from the bottom, from the memory concern group, we found that for the female, actually we have the 4 features being identified useful to predict the amyloid status, and 3 of them you can see the MOCA, ADAS, question 8 and 11. And so when it says question 8, that's meaning the subscores, and if it's total, that's meaning the total scores. And so 3 of them from the cognitive, only 1 of them related to the memory. And however, for the SMC, I think for the males, all the features have been included because probably the ordering of the features were not great enough. And for the early MCI, for the males, the memory score, they are 3 of the memory scores were being there, and also obviously the ApoE4 status and age were there too, and the marriage status were there. However, for the females, so the memory score does not predict the amyloid status for the females. So this is kind of a little bit surprising. So that's meaning in the early stages, basically the females, basically their baseline scores are normally pretty good for the females. So that at early stage, the memory does not predict whether they will have the amyloid positive or not. But you can see on the later stage, there are multiple cognitive tests, and some of them are memory scores. They will be highly, they can be used to predict whether that female will have amyloid positive or not. And also the depression score will be, they'll have family history as well. And yeah, this is what we found. I think there are many, many interesting results. Basically, they most likely agree with the literature about the sex difference in Alzheimer's disease for the memory and all the other executive function stuff. And here's some of our references, and we did for the paper we published on a scientific report this year, and we appreciate the support from the grants for this project. Thank you.
Thank you. We have a question from Sue, who is asking, are the optimal models for different outcomes not so bad for other outcomes? It looks, especially for your presentation, again, that they seem to be doing more or less behave similarly. Is that, did I misunderstood that in the, when you had all the different methods, they more or less behave very, very similarly. So, why do we have some methods behaving better than others? Okay.
You mean on the prediction side? Yeah, so I think the obviously you can see when if you are using some of the, let's say, the simple methods, they may not, let's say you just, for example, you just simple use logistic regression. No, but you should use, yeah, logistic regression because the outcome is binary, right? And but there's a big assumption over there is you assume the outcomes are independent, basically the X value, the features, right? But somehow, but because we use the individual scores as well as the total scores, obviously some of them could be correlated. I guess the reason is in the machine learning models, somehow they could capture the correlation much better.
Another question is, how do you validate the final model setup? Why didn't you use elastic net or similar method to choose features?
You mean the how do we validate these models?
Yep.
Yeah, we did use the, so basically we are the model we presented, we use 80% as of everybody. So 80% to 20%, right? And we used, so that's the results we presented. Obviously, we could do as the other presenters use 70%, 10%, and 20%, but that would further reduce our sample size. So we decided, obviously, that was a great idea. Or maybe alternatively, we could use the NACC data to confirm that. But I believe the NACC data probably don't have the depression score. Some of the scores at the time when we checked, because we did ask to do that, but the NACC data did not have that. At least one of the measurements they did not correct.
Okay. I have a question actually, and it's for both, and it's a general question for the machine learning setup. And I have to say, I'm trained as a statistician, but hanging around with epidemiologists, I start getting really interested in selection bias. And we know that a lot of the centers, we have a selection bias, and each center has its own selection criteria. Now, when we use, statistical methods, we try, to use some weighted method to account for this selection bias. But to be honest, I haven't seen much in the machine learning world in this. So, any ideas and suggestions in general, and how we can? I can see how we can easily do it in a single center, but then when we compile data from different centers, and each center has their own, catchment criteria, how do you envisage doing that in applied terms? I don't know who wants to go first.
I think you are right about that, Yorghos. There a lot of work, I think, is in progress to try to bring together machine learning with more traditional statistics, like incorporating things like mixed modeling or longitudinal models that are better developing statistics. So I think that the main strengths of machine learning is that they can deal with large number of variables, deal with complex data set, locate complex patterns in complex data. However, still lacking some development of these techniques that have been developing statistics for a long time. And I think there is research in progress to try to bridge this gap between the two.
Thanks. Koyen, do you want to add anything?
I think I have the same question, but I have another one. So basically, I will follow up with your question. I don't know how to reduce that, but I think there are many issues in the Alzheimer's disease research. That's one of them, obviously. I'm happy to hear the answer from others, but in addition to that, I have another question. So I think when different centers, they have the image stuff, right? And so they doing the PET scan or the other scans. And I'm not sure how they standardize them. So for example, in Boston, maybe you have the version of like version 1 or 2, and then the other one have like 1.3 or something. They have different versions. So what we found is if each time we change a scanner, actually people's brain is getting bigger. So I think that's not reasonable. It should be consistent. So I'm not sure what's kind of is that because of the technical issues, or basically is there any way we can do it better?
I mean, I wasn't really talking about different versions. I was talking more, let's say
about
in Boston, let's say we're interested in TBI and we'll end up having, former NFL players. That's really not a traditional thing that other centers may have. Now, if blindly you start using, what I'm afraid is if you start using some of these algorithms, you may end up saying, professional football players have high prevalence or something like that, just because you have this overrepresentation. Because the selection of certain centers direct specific subpopulations or even specific disease. So that's a problem, I think. And it's not only machine learning, this is a general problem. I'm putting you on the spot because you are, and sorry to do that. There is another, this is more traditional question. I think this is again, did you consider using the whole data set for derivation and using nested cross-validation for described accuracy?
Yeah, we tried to use our own data set at that time. Like we tried to use our Cobri data at that moment. And so I think, obviously I would prefer to use the NACC data for the validation purpose at that time. And I'm still is. And hopefully someday we could spend some time to get the data from NACC and for the validation purpose.
I think that's from me. Any other panelist wants to add anything on this discussion? So let's gain. If not, let's stop and let's gain this 5 minutes. I think we all need it. Rhoda, it's over to you. Thank you. First of all, thank you all the presenters, the panelists. That was great set of presentations. I really hope to see you all next year in person, so where we can continue having these conversations in person. Rhoda?
Thank you, Yorghos. So Hannah Rosentrader, our main lovely MC, is having some technical difficulties. I'm just stepping in at the very end. I'm the administrator from NACC. If you don't know me, my name is Rhoda. So thank you very much to all of the data core speakers. It was a wonderful session to wrap up our 2021 Fall ADRC meeting. And thank you everyone for joining the meeting and making a big success. Thank you again and have a great day, great weekend as well.